So now we are ready to start to our next talk. Let me introduce Professor Waldron, and you have already shared your screen, so everything is okay. It's again a great pleasure to have you on our conference. He is a professor in mathematics department of UC Davis, and he is also a member of Quantum Mechanics and Physics Institute. He received his PhD degree from Stony Brook University under the supervision of Peter van Nieuwenhuizen. I hope I pronounced it correctly. His first postdoc was at National Institute for Nuclear and High Energy Physics, which is in Amsterdam, and he was working on matrix theory and membranes. Then his second postdoc was at Brandeis University under the supervision of one of the most important figures in physics, who is Stanley Deser, who is also sort of a postdoc supervisor for my PhD supervisor, Tekin Dereli. So in some sense, we have some similarities in our academic family tree, I guess. So he and Stanley Deser worked on higher spin theories, and now most recent works of Professor Waldron are about conformal geometry and other mathematical structures which can be used in physical theories. And for example, today he will talk about contact structures and its relations to quantum mechanics, and his talk will be called Quantization and Geometry. Thank you again, Professor Waldron. The screen is yours.
All right. Thank you very much for that nice introduction. I will say that the introduction is so nice because you guys sent me an email and asked me to write a little introduction. I should have made it even nicer, you know, like very handsome, great jokes, etc., etc. So the plan of this talk is to tell you about quantum mechanics. And quantization. I've got about 20 pages of notes here, and I'm going to take these notes from here and write them down here. I'll try and go nice and slow, so if I don't do all the notes, it's fine. It's better to understand some stuff. Do ask questions, write funny jokes in the chat, all that sort of business. It's a good thing. All right. So we'll start with something that you probably know all very well. What's quantum mechanics? And this is probably quantum mechanics in its Copenhagen interpretation. This is the second time that I'm writing the words quantum mechanics, and that's to prove to you that I know how to spell those words. Okay, so how does quantum mechanics work? You start off with a thing called a Hilbert space, a bunch of vectors in a great big vector space with an inner product. You start off with some state, some initial state in that Hilbert space, and then you wait. So you measure that state, and then you go have a cigarette. And then that state will just evolve under unitary transformations to a new state. Let's call that I of t. The I stands for initial, T stands for time. And then you do another measurement and you ask yourself a question. You say, well, there's some other state called F for either final or favorite. You know, if this was a cat, the initial state would be alive and the final state would also be alive. Right? Anyway, the cat evolves to some final state, I of t. And this is your own favorite state, and then you ask a probabilistic question. I'm writing a bunch of symbols. So you take the evolved state, you take the inner product in the Hilbert space, which will give you a complex number. You square it. Strictly speaking, if you do it right, you better check that the states are appropriately normalized. So you should divide by maybe an F comma F, and an I comma I. I think maybe a square root there, if I get it right. And you calculate a probability. So this is the probability that if you prepare the state in this initial state and you wait some time t, the probability that you'll measure your favorite state is given by this quantity here. So let's drop the normalization. It doesn't matter much for us. And let's write some details of this formula. So how do you get an initial state to the final evolved state? Well, that's by unitary evolution, or the exponential of some Hermitian operator, which we like to call the quantum Hamiltonian. Okay. So the interesting thing to calculate is this this quantity here, which is often called a propagator in quantum mechanics. So here's an idea. So I should say already here, I'm going to show you a bunch of stuff. I'm not going to change quantum mechanics. I only want to change how you think about it. So the idea is the following thing, is this object here, the propagator. It says maybe the propagator maybe this is a Wilson line of a gauge theory. Question mark. Well, that would be a good thing because it would make the title of my talk make sense, right? Because the title was Quantization and Geometry. And Wilson lines are very geometric things. You know, a Wilson line is something built from a connection on some fiber bundle, and you would have some maybe some matter fields or a vector bundle if you want to be more mathematical. So that seems like a good idea to make the title of my talk work, but it doesn't much look like this picture. We're doing quantum mechanics, and I don't really see a gauge theory here at all. So we need to change things a little bit. Right, so to remind you, a Wilson line is a path-ordered exponential. I'm calling gamma a path. It's an exponential of some connection on a fiber bundle. And let's call it a vector bundle. You know, that might be the space where quark fields live, for example. And this gamma is a path in a manifold. And as I said before, we are very distraught because there should be a path in a manifold. I guess there was a path in a Hilbert space before, but I'm not sure that we really saw a path in a manifold on the previous slide. And we didn't see a connection, and we didn't see a vector bundle. So I need to build all those things for you. So let's do quantum mechanics take 2. So this accent I'm using, if you like, I can make it a little more Australian or slightly more American, depending what you prefer. If needed, I can give it a slightly German hint. Those are the 3 possibilities. So you might need to do a poll to figure that out. But anyhow. Oh, right. So what were we doing? We were doing quantum mechanics, and I was going to build you all the stuff of the Wilson line. So I'm going to draw a different picture. The first thing we're going to need is we don't need just one Hilbert space. We're going to need a whole bunch of Hilbert spaces. So for every point in your path, gamma, I'm going to associate to it a Hilbert space H. That's a lot of Hilbert spaces. So now, here's the initial state. Here's your favorite state. And here is the state that the system actually evolves to. And the path I drew before, which happened in one Hilbert space, now jumps from Hilbert space to Hilbert space like that. Okay. Now, this path down here, this is the path labeled by the variable I called t, so time. I want to change that a little bit. And I want to change that for a reason. Yeah, the reason is this. The reason is that just as in general relativity, where we don't all agree on what a clock is, like your clock may not be the same as mine. Like maybe your clock is some combination of my clock and my momentum variable or my position variable. Maybe the same is true in quantum mechanics. And therefore, maybe we should not just have a single sort of time variable, but we should have a whole manifold of possible time evolutions. So I'm going to draw that manifold down here. Okay. So now in this picture, I want you to think this way. So the quantum system is up here. So this is the electron, if you like. The electron is evolving from Hilbert space to Hilbert space doing quantum stuff. And I want you to think that this manifold, whatever it is the classical laboratory. So you should think now generalized clocks, dials and knobs. Just machinery that can measure classical times, positions, and momenta.
So may I ask a question?
Yeah.
So you say this underlying thing is a manifold, right?
Mm-hmm.
So there are different paths and there will be different time labelings for our evolution.
Right.
So do you have, for instance, would this manifold change from the physical system that we're looking to another? Does this make sense? Because is there a dimension of it, or?
Yeah, so two things. First, I'll change your question a little bit. This is the classical laboratory down here. So this is us. This is just a bunch of settings on your dials and knobs. So to each possible quantum measurement, to each possible classical measurement you make, you attach a Hilbert space. And then you might get angry. You might say, oh, well, does it matter which path we take in the classical system? It had better not. That shouldn't change the answer for the measurement. Secondly, which manifold should we put down there? Well, if we have a quantum mechanical system that comes from the quantization of a classical system, that manifold down there had better know about the classical system and the classical dynamics. Right? So if we're describing a particle in a circle, it should maybe have an angle. It should have one momentum-like variable to describe how fast the particle's going on the circle. and it should have one time-like variable to describe when things are happening.
Okay,
A different system would be something different.
thanks.
Okay. Yeah, so let's probe this manifold. Which I think I like to call the manifold Z. Okay. So my answer to that is it's the classical lab, the classical laboratory. So generalized clocks, positions, and momenta. Positions and momenta, we like to call phase space. Clocks and positions, we use that manifold in physics a lot. We call that space-time. So in fact, maybe this manifold should be a phase space-time. So it's a manifold. So in classical mechanics, we like to make a manifold out of positions and momenta all the time. That's called a symplectic manifold. And the moment you have a manifold, it's great because the way you set up a theory no longer depends on coordinate transformations. Just because you label a configuration with some variables and I use some other variables, it doesn't matter. The configuration is the same. It's a point in the manifold. It's just your choice of coordinates that changes. If you work with a phase space-time, you put time on the same footing as positions and momenta. And I'm saying that this is a very good thing to do because you'll be able to do quantum mechanics in a way that doesn't depend on some choice of clock. It'll work for all possible choices of clock. Okay. I'll talk a lot more about that manifold and classical dynamics done on such a manifold soon, but let's now ask the question, which bundle, in more detail. So which bundle, and it's going to be a vector bundle. So a vector bundle is the structure where you have some base manifold. And to each point in the base, you attach some vector space. The classic example is a tangent bundle of a manifold, where you have all possible vectors or directions that paths could go in attached to each point in the manifold. Okay, here we'll take a bundle whose fibers are Hilbert spaces. That means we're dealing with what's called a Hilbert bundle. Over Z. And then you want to think about what gauge transformations you're going to make on this bundle. And that's called the structure group, if you prefer. So gauge trafos. And the answer to that is going to be a very big group. So if you have a vector space V and you write U of V, a complex vector space, for example, if you did C to the n, U of n, that would be just unitary matrices of size n by n. Here I have a quantum mechanical Hilbert space, so I want my gauge transformations to be all possible unitaries. I'll write a formula soon, which will make more sense of why I would want to write that. Okay. All right, so now let's put this all together into a definition of a structure, which I want to call a quantum dynamical system. And the talk will mostly be about how to get quantum dynamical systems from classical mechanics. Okay, so the data for such a beast. Oh, I should say, I should name this guy. I'm going to name this bundle HZ. Just like you write TM for the tangent bundle over a manifold, I'm going to write HZ for a Hilbert bundle over a manifold. So it's a bundle of Hilbert spaces. Incidentally, a bundle of Hilbert spaces, if you have a bundle, you should think what sections are. If you have a tangent bundle, you care about vector fields. What are sections of a Hilbert bundle? Sections, question mark. Well, the wave functions. Wave functions, so remember in quantum mechanics, we have wave functions. Well, they'll depend on a bunch of variables. If your Hilbert space is L2 of R, one of the variables will be X. That X variable has to do with the fiber. But if you let the wave function evolve, it will be also a function of T. And that T you are now thinking of as being a base coordinate. And in some sense, psi of X comma T is a section of a Hilbert bundle. Okay, segueing back, quantum dynamical system. It's the data of a Hilbert bundle and a connection. Yep, question? I think that was not a question. It might have been a comment.
No, it wasn't.
I think I'll continue. Remember that what is a connection, by the way? So if you have a tangent space in general relativity and you've got vectors.
Before you proceed, can I just ask one simple thing? Your manifold Z have as coordinates besides T, both positions and momenta.
Yeah.
So your wave functions should depend on both positions and momenta. It's not the usual wave function.
Yeah. This is interesting. This is bigger than the normal way of thinking about wave functions, right? So normally you would think of wave functions. You would think to yourself, well, in classical mechanics, there's time, positions, and momenta. Then you quantize, and the wave functions, you would pick a polarization in the symplectic manifold. The symplectic manifold is the positions and momenta, and the wave functions would depend on half of those.
Yeah.
In the quantum mechanics textbook, usually they start off with X.
Yeah.
Position. So wave functions would be a function of position, and then actually also a function of time.
Yeah.
Now in this picture, down here, a point here, Z, that is a position, a momentum, and a time. Wave functions, or elements of a Hilbert space, if this Hilbert space is L of R, then elements of this would be some functions of some variable S. I don't want to use the variable X again, because in principle, this is a different variable. So sections of this, so wave functions, the really sections of this bundle, are going to depend on the base point Z and some fiber variable S, which you're using to make the space L2 of R. So it's really psi of position, momentum, time, let's write a semicolon, and some, if you like, it's a fiber position. Right? So it's almost as if the position appeared twice. Or another way that, go on. Oh, I was going to say another way.
You go.
Another way to think, just think of this as psi as a function of Z, but taking values in the Hilbert space. Right. The question?
Can I make a comment? So is this in the
Sure.
same spirit as the Donder-Weil formalism sort of thing for the fields though, in that case? So you have a configuration bundle, then on top of that, a momentum bundle, but underlying all of that, there is some X's, P's, but no T's, if I remember correctly, but just a T, in case of which field theory you're looking for.
I don't want to say for sure, because I haven't thought about that. It sounds similar.
Okay, maybe I can ask it later then,
Right.
in more detail.
All right, we were back doing stuff about this quantum dynamical system. And I was talking about connections. So if you've got the tangent bundle, at each point in the tangent bundle, you can have vectors. And then in general relativity, for example, you have a connection. Would be the symbol nabla here. What is the job of a connection? Well, the job of a connection is to move a vector from one place to another, holding it parallel. So you should always think connections do the job of parallel transport. So this connection will have a connection form, and it'll look like D. Some exterior, this is the exterior derivative on Z. And there'll be some one form living in omega Z. But the one form will also be an operator on the Hilbert space. So it's a Hermitian operator, Herm on H. Now, I mentioned before that I wanted the system not to depend on the path we took in the classical laboratory, because I want the quantum system just to evolve and ignore us. So how do you make evolution be independent of the path you take? Well, if you want paths to evolve in a way that, if you want parallel transport to not depend on the path you take, you should ask a connection to be flat. So I'll require that nabla squared is 0, flat. So this is path independence. And then evolution, quantum evolution will be parallel transport. Or in equations, you solve the equation nabla on psi is 0. Let me just leave that there for a second. That's a parallel transport equation. Or going back to my picture, here's the underlying manifold Z, make it look interesting. You have the Hilbert space here, H, you have some initial state here. You have some evolution of your dials and knobs, some path in the laboratory space. And the way you get this initial state to the final state is you evolve it using a Wilson line. The job of a Wilson line is to solve the parallel transport equation. So this is parallel transport. If you call this object psi, the Wilson line solves the equation nabla psi equals 0. That's the whole point of the Wilson line. Yeah, and then you take the initial state in this picture, you parallel transport it over to there, you compare it to your final state, and there's your propagator. So in this picture, quantum mechanics is formulated in terms of Wilson lines in a gauge theory. Okay. This is a great point to stop. If anyone needs to brush their hair, do something like that. If anyone wants to ask a question, whistle a song. Are there any questions or comments people want to make? It's also a great time if you have a cat, let the cat wander across your desk. I think that's always good.
Where did time goes into this formula?
Right. Time in the laboratory would be, if you have a path, you can think of a path as a function of some variable tau.
Oh.
But there are choices of this variable tau, let's call it tau. There are choices of time, because this manifold here is labeled by positions, momenta, and times. So, you know, this is a bit like how we do relativistic particles. The path would have some parameter, that would be your world line time. The phase space-time also has a time variable, that would be your target space-time. So time appears in two places, but it appears in a way that's generally covariant. A Wilson line doesn't care how you parameterize the path. It only cares about the shape of the path. And because Z is a manifold, it doesn't care which coordinate you call time. I could use this variable as the time if that worked for my particular experiment. So really the question is, does that notion of time match with the clock that you have on the wall in your laboratory? Right? Okay, I think all the cats have walked across your desks. Are there a lot of cats in Istanbul?
Yeah, a lot actually in some regions.
In the streets, yes.
Yeah. You know, when cats can be seen in the streets, that's the sign of a nice place. That's my theory. In some places, the cats are all hiding away. All right, so let's talk about how this picture relates to quantization now. So I'm going to be doing a lot of classical mechanics in a slightly strange way. So to talk about quantization, I need to talk about classical mechanics in a different way. So classical mechanics, take two. Okay. So you might be used to classical mechanics taking place on a symplectic manifold. That's some even dimensional manifold. I'm not saying that's wrong, but I'm saying it's not good. I'm saying instead you should use an odd dimensional manifold. Here's a picture of it. Could be a complicated manifold. It might have a boundary or not. That's an interesting question. It might be compact or not. It kind of depends on the system. It's a manifold Z, which is the phase space-time. And it's the manifold of all possible wheres. Where are you? Or where is the particle? Where is the system? All possible momenta. So I would say where to? Where are you going? Because your momentum tells you which direction you're headed and how fast. And all possible time. So all possible whens. So this is the where to, when manifold. And if you had such a manifold of all possible wheres, where to's, and whens, what would dynamics be? So classical dynamics, well, that would just be a curve in such a manifold. So if you start at this point, that's where you are, but it also knows where you're going, and it also knows when you are. And you drew a path like this, well, this is the story of your life, because you'll move around in some way. And later on, you'll be over here heading in some other direction at some other time. And this is enough data to tell you what you're doing to determine a classical mechanical system. Okay, so dynamics is curves in Z. And then the question is, so what we should do is just write curves all over this manifold. We should foliate it by curves. And all possible curves will be all possible classical evolutions. And now we need to find these curves or describe them. Okay. So one thing you could do is just tell me all the curves and we'd be done. But we never do that in physics, because that would mean you'd globally solve the system. In physics, you need a local description. So local description of curves. So to locally describe these curves, I claim you need a little more data on this manifold. You need to make this manifold into what's called an odd symplectic geometry. So the manifold is odd, so I write Z2n plus 1. It's got 2n plus 1 coordinates, if you like. In a symplectic geometry, what you normally give people is a 2 form. Or if you prefer, if you invert that two form, you give them Poisson brackets. Okay. So for an odd symplectic geometry, you do the same thing. You give a two form. Let me get to Z, it's a two form. You could imagine having an odd dimensional manifold and an electromagnetic field strength. That might be an odd symplectic geometry. Now, in symplectic geometry, you ask that in symplectic geometry, there's two form, which I'm calling phi, and I will call it the Levy two form in the context I use. In symplectic geometry, they call it the symplectic form, and they ask it to be closed. You should ask phi to be closed as well. In symplectic geometry, the other thing you have to do is you ask that the symplectic form be invertible so that you can make the Poisson bivector and calculate Poisson brackets. A two form is anti-symmetric matrix. And in odd dimensions, anti-symmetric matrices are never invertible. They always have a row of zeros in a good basis. So instead, what you do is you ask it to have maximal rank. You ask it to be as invertible as possible. In this case, we'll ask that the rank of that matrix is 2n. Okay. Now, if you're a local person and you have this curve, this is a curve gamma, what you would really want is to have an equation that tells you about the tangent vector rho, tangent vector. And my claim is this data of an odd dimensional manifold equipped with a maximal rank 2 form is enough to determine tangent vectors to curves. Once you know the tangent vector, you can solve for the curve. Once you have the curve, you have the dynamics. Okay. So to find curve gamma, I need a vector field. I need a vector at every point in the manifold. So I probably should have drawn that picture. I need a vector everywhere so that no matter where I am, I know how to draw curves. And then you just solve the equation that the tangent vector, so gamma dot, is equal to that vector field. Right? That's this picture. Here's gamma. Here's the vector field rho. Here's gamma dot, the tangent vector. And I want the tangent vector to match the vector field rho. Notice that f rho, where f is a function, a non-zero function on the manifold, would be equally good. You know, if you have a vector field and you make the vectors a little longer in some places and a little shorter, that won't change the curves that the vector field determines. Because to calculate curves, you just need to know the direction. That's an important point to notice. And then let's observe something. So to find rho, we can write an equation built from the data I've given you. So phi is an anti-symmetric matrix. Let it act on the vector rho. Then there'll be one slot of the matrix or one index left open. If you like, I'm writing phi I, j, rho I in indices. Set that equal to 0. So you get a covector's worth of equations. This has a unique solution. Because, well, I asked that the matrix phi had maximal rank. It's not invertible because it's odd. So it has one eigenvector with eigenvalue 0, and that eigenvector is rho. Has a unique solution because it's max rank, and unique up to rescaling. You can always multiply an eigenvector by an overall function. So the data of a odd symplectic manifold, an odd dimensional manifold with a 2-form that's closed and maximal rank determines dynamics. You might ask why I keep asking that it's closed. I do that for a physics reason. You could drop the closed requirement if you only want the curves, but if you want to do physics, having phi closed is good. So we ask that d phi is closed because then locally, not globally, but locally, phi could be written as the d of alpha, where alpha is a 1-form. It's a bit like electrodynamics. We're writing that F is the d of an A. Sometimes in electrodynamics, if is a in odd dimensions, is an odd symplectic mechanics. This is good. 1-forms are great because 1-forms are the objects that can be integrated along paths, which means we have an action principle. Ooh. I realized I forgot to ask a question. Now this is a 3-hour talk, is that right? No.
Actually, you are out of time, but it's the last talk, and we are like
okay,
prepared for this long talk, so it's okay for you to continue, I guess.
Oh no, I won't continue for a brutally long amount of time. But
yeah,
maybe just say 1 or 2 more things.
Okay, it's up to you. You can continue
right.
many minutes as
okay.
you want.
So you ask this thing to be closed because then you have an action principle. And the action principle is just this. You integrate to the action should be a function of the path. You integrate this 1-form alpha along the path. And then that gives you an action. And then you vary this with respect to gamma. Then that gives you your dynamics. And so then the question is how to quantize this structure. So what I'll do is I'll give you a bit of a summary of what you do next. Okay. If you're given an action principle and you want to quantize it, the first thing you have to check is its gauge invariances. Well, what's the best way to handle gauge invariances? Well, what you do is you introduce a BRST operator. This action has at least one gauge invariance because you could always reparameterize the world line. Secretly, it also has gauge invariances always go with constraints. Secretly, this system also has a gauge invariance as a first-class constraint. Secretly, it also has 2n second-class constraints. And if you're good at constraints, you'll know that you can change second-class constraints into first-class constraints by working in a bigger manifold. That bigger manifold underlies that crazy Hilbert bundle that I wrote for you before. It would be a manifold that has the kind of coordinates that Hilbert bundle had. Okay, so this thing, if you deal with it correctly, has 2n plus 1 gauge invariances. To handle gauge invariances or constrained systems, you should introduce a BRST operator. That's an operator that squares to 0. So first you introduce a classical BRST operator, classical. And then you quantize that guy. The BRST quantum operator comes with a BRST Hilbert space. You have to calculate a bit to figure this out. This is BRST technology, but you do it. The BRST Hilbert space for this simple system ends up being exactly that Hilbert bundle that I showed you before. Then you can now guess what happens. If the BRST Hilbert space is the space of sections of this Hilbert bundle that I wrote before, then which operator could this nilpotent BRST operator possibly be? Well, the BRST operator is precisely that connection. If you do BRST, you have ghost numbers. Ghost number is form degree. So you have differential forms on that Hilbert bundle that I wrote before, and the different differential forms, that's the ghost degree. At ghost number 0, the BRST cohomology is equal to physics. At ghost number 0, you just have to write the equation Q BRST on psi equals 0. Well, that's precisely the parallel transport equation that I wanted to write. i.e., the structure you get is a quantum dynamical system. So the picture I drew for you before, where quantum mechanics was made completely coordinate invariant, choice of time invariant, et cetera, does come from the quantization of an odd symplectic manifold. An odd symplectic manifold, that structure is big enough to describe basically any classical mechanical system you want. So you can quantize any system this way. And these quantum dynamical systems are nice. They have a very large group of gauge transformations, this U of H that I wrote. And having a lot of gauge transformations is usually very good, because it means there are lots of equivalent ways of solving your problem, or problems that you thought were different are actually gauge equivalent. So this is very powerful. There's a lot of stuff you can do with that kind of structure. I don't think I have time to tell you all about it, but people can ask questions. So this is probably a good place to end the talk. Thank you.
Okay, thank you very much for this enlightening talk. Are there any questions? I guess Tekin Hoca has one.
Well, I wonder, on the phase space, we have the Moyal quantization. Is there any relation to Moyal quantization here?
Yeah, that's right. So you might think, my wave functions were sort of depending on positions and momenta, and that smells a bit of a Moyal quantization. Or there's another version of that for more general Poisson structures or symplectic manifolds called Fedosov quantization. And the answer is yes. So if you've got a connection and it's acting on a vector bundle where I had wave functions, you could think of those wave functions as being matter fields. But in Yang-Mills theory, we don't have just matter fields, we have other representations of the gauge group. We could also have fields living in the adjoint, right? The adjoint representation, or the adjoint bundle here, would be fields that are themselves operators. And then you can solve a parallel transport condition for fields in the adjoint. Solving that kind of parallel condition will allow you to solve for operators. It will also allow you to solve for, it allows you to do the following thing. It allows you to, given a function on the manifold, quantize it into an operator. And then it will also allow you to multiply those two functions and quantize that into an operator. Yeah. And so that will give you the Moyal quantization and the Moyal star product. So that structure is hidden in here, but you just need to change the bundle from fundamental to adjoint and then think about parallel transport.
Okay. Yeah, okay, thank you.
Okay, any other questions?
I can ask one.
Yep.
Sure.
So if you look at your base space, the Z, then you have 2n plus 1 coordinates, you said. So if you decide to pick time direction, say our usual t,
Yep.
then you would have some slicing of this, right, into 2n dimensional usual manifolds, usual coordinates, QMPs. And I believe you should have some symplectic structure living in those slices, which are compatible to each other, which tells you that Z should be itself a bundle in some sense. Maybe.
So I very quickly an equation.
Yeah. So this is
So
your contact structure.
This is an example. So I didn't exactly tell you what makes this. This was odd symplectic, but to make it contact, you need to put an extra condition on this alpha. That a certain volume form built from alpha is non-degenerate.
Yeah.
So contact's a special case. But this is odd symplectic. Now let's do an example. Suppose alpha was PDQ minus H dt. And then let's do exactly what you asked. Let's look at slices of constant t. Then you have PDQ. Well, if you take the d of PDQ, you get dp wedge dq, and you'll get standard classical mechanics on each slice. So yes, a symplectic structure is hiding there. And that is, if you look at each slice, that's where this Moyal quantization would live. And that's why I was doing parallel transport to get myself back to the Moyal quantization when I was explaining that stuff. But for this example here, if you then write out its quantization, calculate the BRST operator, and then write out the equation nabla psi equals 0, you will find that this is secretly the Schrödinger equation of a quantization of that Hamiltonian. So the standard symplectic picture is sitting inside of all this stuff. Like I said, I was never going to take regular quantum mechanics away from you. It's just going to make it feel different.
So one could reach your picture maybe by taking the contactization of the usual classical mechanics.
Yeah, there are pictures where you go from contact manifolds to symplectic, or from symplectic to contact. Both those directions can go. But by the way, if you think this contact looks interesting, Arnold's classical mechanics book has an appendix on it, which is worth reading.
I'll check that out.
Arnold.
Thanks. And
Any
thanks
other
for the talk too.
questions?
Yeah, I'd like to ask a few questions.
Sure.
Hi, Andrew.
Yep.
So you basically introduced time to phase space. How does the good old Bohr-Sommerfeld quantization condition change in this picture? Like, I'm assuming it doesn't change in any way, but if you naively integrate your own form, now there's an extra factor. Does that say anything about time-dependent Hamiltonian systems for the quantization condition?
Yeah, so there's a bunch of stuff going on here. So firstly, if this guy is contact, then from this object alpha, you can form a volume form. From that volume form, you can now do integrals over the underlying contact manifold. And then you can form some kind of integral, like do Bohr-Sommerfeld, where you integrate PDQ and ask that that guy gets quantized. So those sort of structures are there. If you're into a thing called geometric quantization, then they have a business like that. And they have also a connection, but they put a connection on a symplectic manifold, and their connection looks, so on a symplectic manifold, you write that omega is the d of a lambda, and their connection is nabla plus lambda. And then they think about integrating this one form around loops to get Bohr-Sommerfeld, or they call it the metaplectic shift. The connection I'm writing, the first term in this connection, so this nabla is d plus alpha. You can think of this as being this lambda, but for me, I write then plus more. But hiding inside the connection I write is a connection like what you get in geometric quantization. And then this metaplectic correction, or the Bohr-Sommerfeld rule, that is sitting there. So that structure is there as well.
Is there any direct physical significance to that? I mean,
Oh,
like thinking of like more concrete terms, like could that be interpreted as a correction to the, I don't know, energy levels of some bound system?
right. So where does all that quantum stuff come from? So there are two stories that I kind of hid here. I said I wanted a flat connection so that we had path independence. Suppose your manifold Z looked like this, and I parallel transported around this path and that path, and there was a hole in my manifold. Then I would have been wrong. I would have been wrong about the path independence because I would pick up a holonomy. I would integrate the Wilson loop around a hole and pick up a holonomy of the manifold. That holonomy is an operator. I still need this path independence. Otherwise, my experimental results would depend on what the laboratory did, which we don't want, right? So in fact, you'll get some holonomy operator, hol, and you find what you must do is you should take the BRST Hilbert space and you should divide out by that holonomy. Dividing out by that holonomy will give the quantization of states. So quantum effects like getting, like suppose I was doing a particle in a circle and the momenta come in discrete jumps. That comes from an effect like that. There's another effect that gives a quantum effect is if you really want to go from a classical mechanical system to a quantum one, I have to solve for the BRST charge. And solving for the BRST charge in such a way that I get an operator on the Hilbert space, and that operator makes sense. So there's a thing called formal quantization where you solve order by order in H bar. And there's a full quantization where you get an exact solution in terms of H bar. That jump from formal to solving exactly for the connection, that will also give quantum effects, like getting finitely many states or energy levels, stuff like that.
And in the beginning of your talk, you mentioned about Feynman propagator. When you talk about Feynman propagator, it's inevitable to talk about path integral. So it's just a sort of a naive question, but that BRST condition that you wrote down, is there any straightforward connection to the path integral measure?
Sure, right. So you could have said to yourself, I'm going to now calculate the Feynman propagator for the action principle I wrote down. You would say to yourself, oh, I'm going to do that with a path integral. That's a good plan. But there'll be a problem because it's gauge invariant. So you can't just integrate over all the field variables. The thing just blows up in your face in a way that doesn't make sense. How do you fix that? You fix gauges. How do you fix gauges properly? You do BRST. So you could have found exactly this picture by thinking about the BRST quantization of that path integral. There's a second story about path integrals here as well, and that says the following: the path ordered exponential of a Wilson line, a path ordered exponential of an operator. How can you handle such a thing? Well, such a thing can be handled nicely, or even defined if you prefer, as a path of the Wilson line operator itself.
Okay, I mean, when you look at it, it's kind of hard to see.
But that's just math talk, right? Here you have a physical reason why you need flatness, because the BRST operator is a connection in this picture. And then this gives you path independence, which we need for physics.
Thank you.
Yep.
Any other questions?
This is maybe a far-fetched question. So I want to ask you, are you positing like the fundamental object is have the dimensions of space, time, and momentum? And does that mean the momentum gave some geometric significance, or is there some fundamental difference between space-time and momentum?
I'm saying that those should be all on the same footing. I'm saying that you should allow yourself to do coordinate transformations that swap time with position, or swap position with momentum. Swapping position with momentum we do in quantum mechanics all the time, because you can have wave functions that are a function of position, you Fourier transform, and they become a function of momentum. You can have momentum space wave functions. So that can be done. Why would time be on a very different footing to positions and momenta?
True. I guess my question is not directly related to your talk, because I was also asking about phase space, the old idea of having momentum and space together. Does that mean momentum gain the geometric significance of space, or they're just different kinds of things?
I think it sort of does. I mean, we learned a long time ago that we had to put space and time together to do general relativity properly. We learned a long time ago that to do classical mechanics properly, you should put positions and momenta together into one covariant structure. Stands to reason that you should actually put both those ideas together and put position, space, and time all together in one big manifold that I called Z on the same footing, and have a covariance property with respect to positions, momenta, and time. And if you think about setting up laboratories and clocks and dials and knobs and rulers, we in fact do that. Like your clock could be a combination of my clock and my ruler. You know,
is there a neat term for the distance in this new space?
Yeah, so this space doesn't have a metric, but if it's contact, so you have this one form alpha, it does have a volume. And it's very important to have a volume to have a measurement theory. So if you say that you're going to measure position, space, and time, it doesn't make any sense unless you can put error bars on those measurements. To put error bars on a measurement, you have to have a notion of a volume of a small region. So if I measure, you can never measure an exact point. You only measure approximately just a region. And you need to be able to say how big that region is in your parameter space. So the space needs to have a volume. So when Z is a contact manifold, it does have a volume. Incidentally, that volume is preserved under the evolution. There's a Liouville theorem for that guy.
Can I ask, how would you couple an electromagnetic potential to your wave function? Do you have a complex structure?
Yeah, so you are second quantizing on me, and I'm only doing quantum mechanics.
Okay.
But you
the
could...
reason I ask, you have a symplectic structure, and if you have a complex structure, then that gives you a metric structure.
Yes, that's true. That's true. And sometimes there's a metric in town. One of the gauge transformations is the change of phase. And so you could, I mean, that question would make sense. I've got a connection. You could twist that connection by an electromagnetic potential and then add an extra gauge transformation for that if you wanted.
Well, you have to, you want to couple to the electromagnetic potentials for physical reasons.
So suppose your classical mechanics was a system of an electron or some number of electrons, not second quantized, but first quantized, many body, moving in an electromagnetic potential. You can write down the Hamiltonian for that, and you could write down an odd symplectic manifold describing that. Okay. And part of the data would be that background electromagnetic field. That you could do, but that would be just a matter of writing down the right alpha. There's a slightly different to the thinking where you're going to second quantize this business.
Yeah, okay, I think that's what I asked. Yeah.
Okay. Any other questions? I have still some, but we are really out of time. If you need to leave or want to leave, we can finish the session, or otherwise I can ask my questions. It's up to you, Mr. Waldron.
If you want to ask a couple more questions, I'm happy to answer. And if people need to go look after their cats, that's also fine.
You're a quite cat person.
Actually, I'm sitting in a room with 2 dogs.
To
So the cat is upstairs.
Yes. Let me ask my question. That you said that q square being 0 is implies that the connection is flat. But what about for example, torsion of the connection? If the connection is torsion free, what does it say about the BRST operator?
Right. So you are now thinking in terms of an affine connection, and then torsion has something to do not with, well, it's to do with parallelograms closing, right? For an affine connection on the tangent bundle. So you would be interested in some equation like nabla. Well, let's write nabla is equal to A times nabla plus B. And you would think of this as your torsion, maybe, right? Thinking of that as torsion in this generalized setting, well, I'm asking that this vanishes and this vanishes. B would be the curvature. So generalized torsion in that sense vanishes for this connection. But remember, this is not really an affine connection on the tangent bundle. This is a connection on the Hilbert bundle.
I see. It's still, we can define some notion on any vector bundle, but let's not.
Yeah, but this vector bundle is, it's not the vector bundle where you write, it's not the tangent bundle where the standard torsion lives, right?
Yeah, I see, but for other kind of connections, we can also define some torsion, but it's not related to our torsion at the moment. So let me.
So I guess you might ask the question, suppose my Hilbert space was finite dimensional, which can happen. And then my Hilbert space would be not infinite dimensional, but finite dimensional. My Hilbert bundle could be the same dimension as a regular tangent bundle. And then could it ever be that the connection I write down is an affine connection? And could that bundle be the tangent bundle? I don't know whether that could happen. It's perhaps not a silly question to ask. And then once you've done that, you could ask your affine connection torsion.
Yeah, I was actually asking because the BRST operator acts like the exterior derivative.
Yes.
And we can use it into, we can put it into sort of like Cartan-Magic's formula to get a sort of generalization of Lie derivative.
Yes.
And then by using that Lie derivative, we can define the bracket. Then by putting that bracket into the definition of torsion, we can define the torsion, but it's quite a long way. I was meant to ask that, but
I think no, that makes sense. I can tell you part of that story. So suppose you wanted to, so here I have a quantization. So the idea here is that once I hand you the manifold Z, odd symplectic, or maybe contact, and I build you the nabla. So that is meant to be my quantization of that system. Then you might ask, oh, I have some interesting charge or some conserved charge to do some symmetry, perhaps. How does it get quantized? Well, to answer that question, yes, you should do what you just said. You should think about, well, this connection nabla is equal to D plus more. And you know by the Cartan magic formula that the Lie derivative is intimately related to the exterior derivative. So can you build a generalized Lie derivative? And the answer is yes, you can. And thinking about generalized Lie derivatives is how you get quantized charges. So, you know, you would have a charge that generates a symmetry classically. That symmetry will be a vector field. And now you want to have generalized Lie derivatives along that vector field and build charges. So yes, you can do that. Then having done that for that generalized Lie derivative, you can ask a torsion question. And that is a very good question I haven't thought about. But yeah, that is reasonable to ask.
Yes, thank you very much.
Yeah.
Any other questions? We are quite a lot out of time. I guess we are out of questions, but Jem has one, I guess.
So since we're
Out of questions, out of time.
Do you have a question, Jem, or?
Yes, I would like
Okay.
that. So where does the geometric phase live in this picture? I think the geometric phase should be living somewhere in your picture, right?
By geometric phase, what do you have in mind exactly?
The Berry phase. So if
Berry
you move your
phase.
in a closed loop,
Yeah, okay.
you have some flat connection, but
Right. So this great big space of unitary transformations includes just multiplication by a phase.
yes.
And so now you could transport a wave function around the loop and look at whether it changes by a unitary corresponding to a phase. And then that geometric phase must live there.
Okay. Yeah.
So the holonomies for this nabla include that phase and much more.
I can see that now. Thanks.
Right. And then I'm asking all of those to be trivial. And if necessarily, I will divide out by that holonomy. Right. I should say that, I've just taken quantum mechanics and written it in a different way. So everything that's there, take your favorite quantum mechanics phenomena, you should ask how to handle it this way. And you should ask, can I handle it better or worse? And, there are a lot of questions to ask in quantum mechanics, and I've thought about barely any of them in this context. I've thought about some of them. So these are good questions to ask.
Okay, thank you again. I think it was a quite record for the number of questions for a talk in our conference. And we are like 20 minutes out of time. Thank you for everything, Professor Waldron.
Oh, it was a
It
pleasure.
was a great pleasure to get you on our conference. Thank you very much again. And
hopefully we can see each
have a
other
nice
in person soon.
Yeah, I hope so.
Right.
To see you soon.
I hope so too.
Yeah.
Thank you very much.
That would be great.
Especially Jem, probably. would be the
Yeah.
happiest.
He can come here.
Yeah,
That would be terrific too. Right.
soon.
Yeah. Hopefully it's all going to work out. Sweet.
Okay.
All right.
Thank you again. Have a nice day.
Take care.
Professor Waldron, and have a nice day
Bye-bye.
to our audience. See you later. See you tomorrow, actually.
All right.
Okay.
Have a nice day.